In this video, I want to talk about boundaries and the extreme value theorem. Boundaries can play an important role in our optimization problems because sometimes when we're looking for maxima or minima, they don't occur at a turning point, they don't occur at a tangency condition, they occur at the boundary of our function. And it's important to recognize when we should be looking at these boundaries and when we don't need to worry about it at all. And if you look at the theorems that have been discussed in these videos, often they talk about going from an open domain, let D be a subset of Rn and let D be open and F go from D to R. And the reason for this is that we are often excluding the boundary as being part of our analysis so that our optimization theorems that follow in terms of critical points being maxima or minima are legitimate. But in the real world, sometimes we do optimization problems and our domain is not open. It contains boundary points. And if that is the case, we need to consider them in our analysis. So question, what role does the boundary play? And to answer that question, let's look at the examples below. Okay, example number 1. In this case, our function f goes from 0 to 1 and the function just maps x to itself. The domain is not open because 0 and 1 are the boundary points and they're included in the domain. And you can see that our max and min for this function are 0 and 1. And clearly these are not turning points. They're not critical points. They're just the largest and smallest value because it is on the boundary of our domain, and the nature of this function is that it's an increasing function. So global max / min occur at the boundaries. These are not critical points. That's the take-home message there. Our second example is the same as before, except now we've confiscated those boundaries. 0 and 1 are no longer included in our domain. And in these cases, there's no min or max at these endpoints. And you can recognize this because as you get closer and closer to 1, you will always increase your objective function. But any point that you choose to stop at is not going to be the largest point because you could just add the difference between that point and 1 divided by 2 and you will get closer to 1. So you can always increase your objective function by moving closer to 1, but you cannot pick 1 because it's not included in the domain. So there's no max because there's no point that is the largest in terms of to the left and to the right of that point. So interesting how now there's no max and no min and our domain here is open. In this example, the local max and the local min are not necessarily the global max and min because our boundary is going to be the global min in this case, and our local min is not smaller than this boundary point. And our local max is also not a global max because although there is no global max at the boundary, there is boundary points, i.e. all of these ones up here, that are larger in function value than this one. So local max is not global despite being the only max. The extrema are always critical points or boundary points that are part of the domain. Okay, so it's just very important to understand that the boundary does affect our analysis on finding max and mins. Okay, and an important theorem that actually comes out not from this directly, but is definitely related to this, is the extreme value theorem, which is one that we can combine with our boundary analysis to find the solutions to our problems. And the extreme value theorem says this: let D be a compact set that's a subset of Rk, and the function map things from D to R, and that function is continuous. Then F has at least one global max and at least one global min. That's it. So put differently, what this theorem is telling us is that if D is closed and bounded, that's what it means to be compact. And F is continuous. That together is enough for us to know that there is a global max and a global min, at least one of them, at least one for both of these types. We know that it exists. And this theorem is really helpful because if we can apply the theorem and we find no critical points, we then know that the max and min must lie on the boundary because according to the theorem they exist, and if they're not a critical point, they must be on the boundary instead. Okay, so that's it. Maybe one last thing to address here is, why is f being continuous important? I think closed and bounded makes sense. Closed is related to this above, so the domain here is not closed and there's no max or min, so that's a good example for this property here. Bounded, on the other hand, you could look at it as just going on forever. So if it was, if you had this function here, but the domain was just the real numbers, it's not bounded and it will go on forever and it will have no max or min for that reason. Hence why bounded is important. And then continuous, well, you could have something that is closed and bounded, so it goes from 0 to 1. And here there's a big hole, like a volcano, and the idea is that the function, if I just zoom in really close here, the function does have min on these 3 points here, but there's no max, because as it keeps increasing towards the summit, it never actually can reach that summit, because the point is defined here according to a piecewise function. So this would have no global max, but it is closed and bounded because the function is bounded, it fits within the circle, and it's closed because it contains all of the boundary points in this domain here, but it's not continuous and it has no global max. Okay, so I hope these examples just give a bit of intuition as to why these three properties are important. And when we do have these three properties, we can conclude that there must exist a global max and a global min, and then we can apply our solution techniques to find them. All right, I hope you found this video helpful. Thanks for watching.